Okay, so let's go through the multiple choice problems on your review for your exam on hypothesis test for proportions. An opinion poll asks a random sample of adults whether they favor banning ownership of handguns by private citizens. A commentator believes that more than half of all adults favor such a ban. The null and alternate hypotheses you would use to test this claim are, well, so you need one starting value. Your null is always an equal, so you can ignore D, by the way. So our starting value is going to be that 0.5, because they said more than half, but we need a value. We can't use 0.6, 0.7, 0.8, 0.9, all of them. We just need to pick one, and since that boundary is 0.5, that is our null. Now, they're doing research here, and what they're trying to figure out, is it more than 0.5? So our alternate is more than 0.5. E is the correct answer. Number 2, the power takeoff driveline on tractors used in agriculture can be a serious hazard to operators of farm equipment. The driveline is covered by a shield in new tractors, but the shield is often missing on older tractors. Two types of shields are the bolt-on and the flip-up. It was believed that the bolt-on shield was perceived as a nuisance by the operators and deliberately removed. But the flip-up shield is easily lifted for inspection and maintenance and may be left in place. In a study by the U.S. National Safety Council, random samples of older tractors with both types of shields were taken to see what proportion of shields were removed. Of the 183 tractors designed to have bolt-on shields, 35 had been removed. Of the 136 tractors with flip-up shields, 15 were removed. So we have two proportions going here. We wish to perform a test of our null is the proportion of bolt versus the proportion of flip are the same versus the alternate where we truly believe the bolt-on ones are removed more often, so the proportion of bolt is greater than the proportion of flipped. And you can see they define where PB and PF are proportions of all tractors with bolt-on and flip-up shields removed, respectively. Which of the following is not a condition for performing the significance test? So it is important we choose the samples at random. It does say both populations are normally distributed, but we got an issue here. This is categorical data. There is no normal distribution in the sense of, we're not recording numbers here. So this does not apply. B is not a condition for performing the significance test. It is important that data come from two independent samples, and we do need to check the large counts condition that the expected number of successes and failures are large enough, and both populations are more than 10 times the corresponding sample sizes. That's also known as a 10% condition. Number 3, to determine the reliability of experts who interpret lie detector tests in criminal investigations, a random sample of 280 such cases was studied. The results are given in the table. So you can see here we've got what he decided, and here's a true status. So you're either in this world, here, let me get my pointer here. You are either, the guy's either innocent or he's guilty. So when they were innocent, the examiner chose innocent 131 times and guilty 9 times. And when they were guilty, he chose innocent 15 times and guilty 125 times. If the hypotheses are the null is the suspect is innocent versus the alternate that he's guilty, which of the following is the best estimate of the probability that an expert commits a type 2 error? So a type 2 error means that the suspect is really guilty. So that means we are over here in this column of guilty. The examiner decides 15 are innocent and 125 are guilty out of a total of 140. So your answer is B. So why is that the type 2? Again, type 2 means the second hypothesis is true. We're going to ignore this part here. Let me go ahead and cross that out. So we ignore this because we know that this is the true status right here, guilty, right? And so since we're in this situation, what kind of error could we make? The error would be when we chose that a guilty person was innocent. So that's your error right there. Number 4, a significance test allows you to reject a null hypothesis H0 in favor of an alternative hypothesis HA at the 5% significance level. What can you say about significance at the 1% level? So you have so we're trying to figure out when you can reject and when you can't reject. So I find it's easier to go ahead, and I'm just making up a scenario where we're going to say that we're doing the one-sided and to the right. I could do this with one-sided to the left. I could do a two-sided, but this is the simplest one for me to look at. So we're just going to go ahead and pretend that our alternate is something that our value is greater than some value or more. So we're on the high end. So if we have a 5% significance level, that means that our rejection area is over here. And that means my z-score is anything from 1.645 and up. That would result in rejection. Now, if I have an alpha of 1%, that shifts the z-score further to the right. So now we need an alpha, now we need a z to be greater than 2.3263. So if the z-score is between these two numbers, if it's from the 1.645 to 2.236, we're going to reject at the 5%, but not at the 1%. If the z-score is further to the right, say it's at 3, then it would count in the rejection area for both. So the problem is, since we only know we're somewhere in here between 1.645 and to the right, we don't know that we're all the way to 2.3263. So we're not sure if we're in that kind of in-between area or area to the right. So we can't determine from the information given. Number 5, a random sample of 100 likely voters in a small city produced 59 voters in favor of candidate A. The observed value of the standardized test statistic for performing a hypothesis test of the null is p equals 0.5 versus p is greater than 0.5 is which of the following? So our standardized test statistic is our statistic minus our parameter and all over the standard error of the statistic. And remember, from our math chart, that's the formula for standard error. In this case, let's see, we're doing a hypothesis test, so I'm using the sigma. I'm not using the SE, even though that says standard error. I guess they don't want to say standard deviation. It always tends to say standard error. Okay, but we're actually going to use the sampling distribution standard deviation because we have a hypothesized value. Okay, so we're going to go ahead and put in our statistic, which they said was 59 out of 100, so that's 0.59. And then our parameter is 0.5. And our standard error, well, I'm just really standard deviation, I'm substituting in 0.5 in both places and 59, and you find out that matches choice A. Number 6, a researcher claims to have found a drug that causes people to grow taller. The coach of the basketball team at Brandon University has expressed interest but demands evidence. All right. Over 1,000 Brandon students volunteered to participate in an experiment to test this new drug. 50 of the volunteers are randomly selected, their heights are measured, and they are given the drug. 2 weeks later, their heights are measured again. The power of the test to detect an average increase in height of 1 inch could be increased by, now they don't say bigger sample size, so that's usually our magical solution, right? They're talking about different alphas. Using only volunteers, that has nothing to do with it. Smaller sample size, bad. Using a two-sided test instead of a one-sided test, well, that wouldn't make sense because, actually it makes it worse, because we're basically trying to make sure that we want an increase of more than 1 inch. We don't want our people shrinking, so E is not applicable. So let's go ahead and look at the alphas. So if I have an alpha of 0.05, right, so this is my hypothesized mean, and my true value is somewhere to the right, okay? It could be here, hopefully it's not. Hopefully it's out here somewhere, right? Well, the more my sample, if I were to draw my true value, let's pretend I draw it here. Well, I'm actually going to draw it. We're not going to pretend. It's going to be a horrible drawing. Sorry, guys. Let's pretend that that is my true value. Oh, that's not so horrible, right? So basically the power is the ability to reject. So if we're over here, right? So if I use an alpha of 0.01, right? Let me go ahead and do this so I can highlight. Then this is the probability of rejecting. So that's my power, right? Now, if I go ahead and use an alpha of 0.05, let me go ahead and change the color on this. Highlighter, ink color, there we go. We'll go red. So if I do alpha 0.05, all of a sudden I'm also adding all this area in, and my power has increased. So you can basically see that using a higher alpha, which means we're going to be less likely to change our mind on the null hypothesis, it will help us. Again, remember, power occurs when HA is true. We want to be more likely to reject H naught. If we use alpha as 0.05 instead of 0.01, then the probability of rejection goes up. Sorry, you can't see that because of my highlighters there. So our answer is A. Number 7, a 95% confidence interval for the proportion of viewers of a certain reality television show who are over 30 years old is 0.26 to 0.35. Suppose the show's producers want to test the hypothesis P equals 0.25 against the alternate that P is not 0.25. So this is a two-sided hypothesis test. Which of the following is an appropriate conclusion for them to draw at the 0.05 significance level? Now, a 95% confidence interval does match beautifully against a two-sided hypothesis test with 0.05. Why is that? A 95% confidence interval shows plausible values for 95% of the central data, and it rejects values in the most extreme 5%. Well, that's the same thing as a two-sided hypothesis test with alpha 0.05. Now, so we can just use this interval as is. Is 0.25 in our interval? No, it is not. So we're going to reject our null hypothesis because we have convincing evidence that the true proportion of viewers of this reality show differs from 0.25. Number 8. In a test of the null, P equals 0.4 against HA, our alternate, P doesn't equal 0.4, so a two-sided hypothesis test. A random sample of size 100 yields a standardized test statistic of Z equals 1.28. Which of the following is the closest to the p-value of this test? So, let me go ahead and get my pointer. So we're going to go ahead and do a two-sided hypothesis. So what does that mean? That means we look at the extreme lows and the extreme highs. Now here, because I use Staplet, you can actually see the areas. But let's go ahead and make sure we understand how to do it with our calculator, since you won't be able to use the normal distribution on Staplet. So first of all, on calculators, they don't do an outside area like Staplet does. It's kind of a nice thing. So what we have to do is we have to pick a side. We can either do the left side or we can do the right side, but we're going to double it because it's symmetric. They're the same number. So if I put this in the calculator, I'm going to say 2 times normal CDF. The lower is 1.28, the upper is infinity, the mean is 0, and SD is 1. Why? Because I'm using Z-scores, so we're in the standard normal distribution with a mean of 0 and a standard deviation of 1. So unlike Staplet, we cannot do a two-sided hypothesis like that with the outside area. So we're doing normal CDF because we're trying to calculate probability, and you can see I can only do one cutoff region. So I could do the left or the right. I'm going to go ahead and stick with the right. So it's 1.28 for my lower. And then I have 1, and then you hit the second comma button, then 99, and that's infinity. We're using a standardized curve since we're using a Z-score, so I just hit enter and paste. And you can see I get the matching answer to the Staplet, 0.1003, so really 0.1. So we just double that 0.1003, which gives us 0.2006, which is very close to our answer. that is not what I meant to do. There we go, 0.2. All right, that was interesting. So, next one. Number 9. Bags of a certain brand of tortilla chips claim to have a net weight of 14 ounces. A representative of a consumer advocacy group wishes to see if there's convincing evidence that the mean net weight is less than advertised, and so intends to test the hypothesis that the null is, the assumption is it is 14 ounces, and the alternate is that it's less than 14 ounces. A type 1 error in this situation would mean concluding that the bags, well, if it's type 1, then our null is true. The mean is 14 and the bags are filled properly. But if we're making an error, we think the other one is true, the alternate. We think the mean is actually less than 14. So we think the bags are being underfilled, but they're not. So that would be choice D. Number 10. Hospital administrators wish to determine the average length of stay for all surgical patients. A statistician determines that for a 95% confidence interval estimate of the average length of stays to within 0.5 plus or minus 0.5 days, 100 surgical patient records would have to be examined. How many records should be looked at for a 95% confidence level estimate to within plus or minus 0.25 days? So we're cutting the confidence interval in half. It's the same confidence level, so that means we need to cut standard error in half. So let's look at standard error. The only thing we're going to be changing is that n. Now, because it's in the square root, we need to actually square the factor. So to cut in half, we need a sample size that is either that is 4 times bigger, because 2 squared is 4 times. So we need 4 times 100, or a sample size of 400. And good luck on your test.